Okay. Good morning to everybody. I would like, yeah.
Good morning, sir. This is Amar here.
Yeah, Amar, yes.
May I take a minute?
Yeah, please.
Yeah. So today is 5th September, and I would like this opportunity to say something to you.
Yeah, please.
um, First of all, I would like to extend my deep gratitude and to your guidance, your teaching, and everything, which actually is, all of us here, and maybe be much beyond that, for their learning, which is not only about subjects, about many other things. In fact, I learned a lot during the small period when I got associated with you. So altogether, I would really like to thanks a lot, and yeah.
Thank you, Amar. Thank you very much. And blessings and good wishes to everybody, all the students. Thank you very much. Okay, so we'll begin the lecture. Let me share the screen. Just a minute. Okay, is my screen visible?
Yes, sir.
Screen is visible. Okay. Just a minute. Okay, so today is lecture 4 on probability and statistics for AI. Today, we would like to start looking at central limit theorem, which has been called the crowning glory of probability. I find it said in many textbooks of probability and statistics. And we'll start moving towards hypothesis testing, which is one of the primary goals of this series of lectures. Is my screen visible after I shifted to presentation mode?
Yes, sir.
Okay, thank you. So we'll start with a question in NLP, machine learning, AI. Keeping the test of hypothesis as our goal as we move along. But today's discussion, we would like to work out a problem, and through that working out, we would like to see how the probabilistic treatment of a question can yield practical values in different useful situations. So the question we face all the time in data-driven AI, learning-based NLP, speech, vision processing, is illustrated by a small discussion on part-of-speech tagging, which is, by the way, a very representative problem for NLP. Many large concepts, deep and important concepts, can be illustrated through the simple problem of part-of-speech tagging. This is probably the most elegant representative of sequence leveling problems. So I have the sentence, the black dog barks. The sentence ends with dot, begins with hat. So these are the sentinels for the sentence. The hat symbol is the sentence beginner, dot is the sentence finisher. So they are required because we run a Viterbi algorithm or beam search algorithm, traversing from the hat state to the dot state, finding the most likely path, the path with the highest probability in our quest for the best part-of-speech tag sequence. The part-of-speech tag repository is very simplified. We have only determiner, noun, NN, verb, VB, adjective, JJ, RB, adverb, and OT, others. These 6 tags. And we know from our treatment of mathematics of hidden Markov model that we can begin to we can begin traversing from the start state, which is the hat symbol, and go to the 6 states starting from hat, and each of these states gives rise to 6 states here, and this way there is a search tree which potentially can become exponential. So it can be 6 to the power L, where L is the length of the sentence. But we know that Markov assumption can become our savior. We advance only those states, those paths, which end in the highest probability sequence. So if I come to this node dt, I will get dt from NN node in the previous level, VB node in the previous level, and so on. But the path that ends in dt having the highest probability is advanced further. So at any level, we deal with only 6 nodes. Okay, so instead of 6 to the power L, the complexity becomes 6 into L. This is the famous Viterbi algorithm. Now, having done our sequence labeling on the test sentence, the black dog barks, we look at the result. And in the result, we find hat is given the hat tag, the is given the tag dt, black is given the tag nn, dog is given the tag vb, barks is given the tag vb. Out of these 6 tags, 4 are correct, because black being tagged as nn is wrong. Black is an adjective here, though black from the dictionary can pick up the noun tag. All of you remember that part-of-speech tagging is essentially a disambiguation exercise. Dog also can be a verb and noun, and here we find the tag to be VB, which is wrong, not as per the context. It is not consistent with the context. So 4 out of 6 tags are correct. I take the ratio, get my precision. Precision means how many outcomes are correct. Amongst all the outcomes, how many are correct? So this becomes 66.67%. And now can I jump and say that this will be the behavior for the population? In the sense that the POS tagger that I have built now, for all time to come, it will function with 66.67% precision. This POS tagger for all times to come will have 66.67% precision for any new sentence, any new corpus. So the question is, will it on average tag 67% of the words correctly? That is, we make the question more precise. On an average in the long run, long underlined, 20 out of every sample of 30 word sequences will be correct. Can I claim that? Okay. And my claim was based on just one sentence, the black dog barks, and intuitively, you will immediately come back and say that, no, I don't have confidence in what you say. Okay, I do not have confidence in what you say. So this very intuitive notion of confidence in real life is turned into a very technical question in the form of confidence interval as applied to a normal curve. Okay, so this is a mathematical attempt at capturing the intuitive notion of confidence that we meet every day in our real life. Okay, so we are proceeding towards that formalization. So I'll just repeat this point. I claim I have confidence that my part of speech tagger has accuracy of about 67%. That means it will do part of speech tagging on unseen corpus with 67% accuracy. That means every 2 out of 3 words on an average will be correctly tagged. A very strong claim based on only one sentence, which doesn't seem right. So this is the motivation. And let's see what machinery we have at our disposal from the theory of probability. So this precision question, which asks, is every word correctly tagged or not, is very similar to the coin tossing problem. It's very similar to coin tossing problem. So I toss the coin n times and observe how many times we find or we get head or tail. Appearance of every head is looked upon as correct or success, and appearance of tail is a failure or incorrectness. So then I know that the probability of finding head on an average, if the sample is large, is k by n. This is a parameter for the coin, okay, or parameter for the random variable experiment. Now note the similarity between the two tasks, finding a head and computing precision in a sequence leveling task. Computing precision in a sequence leveling task. Okay, so every head is looked upon as correct. So number of heads divided by number of trials is my precision figure. Okay, and this we know is keep putting us in the realm of Bernoulli trial and binomial distribution. So every toss is a Bernoulli trial because it has two outcomes. And with IID assumption, we know that the probability of k successes in n trials with the parameter p, which is the controlling variable, we have this expression, probability of k successes in n trials with p as the parameter is n choose k, p to the power k, 1 minus p to the power n minus k. Now we know that if we apply maximum likelihood principle on this expression, that means we try to find out the value of p that maximizes the probability of the observation, then we can get the value of p as k by n. Some amount of mathematical jugglery is involved here. We convert the exponential expression into a logarithmic expression. Okay, we apply log on this so that the exponent comes down and sits as a multiplier. So all these are very nice, and the principle operating is maximum likelihood. So we are in the realm of Bernoulli trial and binomial distribution. Now we know that binomial distribution can be given normal approximation. Okay, we can do normal approximation to binomial under this condition. If x is a binomially distributed random variable with parameters n and p, p is the probability of success and n is the number of trials. Then if n is large and p is close to half, okay, and or p is close to half, then x is approximately normal with mean n into p and standard deviation n into p into q, q is equal to 1 minus p. So we'd like to look at the proof of this. We'll do the proof because in these lectures we do not leave anything assumed or accepted. Okay? But for now, we just accept that a binomial distribution can be approximated by normal if n is large and or the probability of success is half, close to half. So once we do that, we come to the realm of normal distribution, where we have a large number of very elegant instruments to deal with, especially the question of interval estimate. Okay, we can give confidence intervals and the probability of being our observation in that interval. So that machinery is available to us. So in particular, if you're interested in 95% confidence interval, that is 5% error, then we know how to deal with the question through Z-score table. So we'll look at it again today. So I suppose what I'm trying to say is clear so far. So we have a binomial distribution. If n is large and p is close to half, we can approximate that binomial distribution by normal distribution. And we can make confidence interval probability estimates. Okay. And this point is important for us because we deal with the ratio of counts. Precision is a ratio of counts. The probability of state transition from noun to adjective, adverb to verb, verb to end of sentence. All these are computed by ratio of counts. Okay. So how much confidence do we have in these parameters computed by ratio of counts? The underlying assumption for all this is that these random variables, namely the random variable of noun following adjective, these follow multinomial distributions. Okay, so we want confidence in each of these parameters: confidence in the precision, confidence in the recall, confidence in F-score, confidence in parameters of transition, confidence in the observation probability. Everywhere I need confidence. And for that, I need a machinery. That machinery is the theorems and lemma with respect to normal distribution. I invoke those. Though my underlying distribution is not normal, I can invoke these theorems and lemma from normal distribution. I can do it when I am in a sufficiently large space. What is this sufficiently large space? Okay, that is told to me by central limit theorem. Okay, we are proceeding towards that. So the hope is that after this discussion, we'll be more knowledgeable or more confident about the claims that we make, the test of hypothesis that we do. We're progressing towards that. Maybe we're going slow because we do not want to leave anything ununderstood. Okay? So here also we face a trade-off situation and we have to do a balancing act. We know that more is merrier. The more testing we do, the more confidence we have in our observations. And we would like to remember we would like to relate to the COVID situation now. Okay, the government is asked to do more and more testing of COVID. The state machinery is asked to perform more and more of tests of corona patients. But testing, we know, needs resources. More testing is more cost. Less testing is more risk. So we have to do this risk-resource trade-off, a point that was our starting discussion in the first lecture of this series. So definitely, if I take more and more corpus and run my part-of-speech tagger on that corpus, compute precision, recall F-score, my confidence in the observation will go on increasing. But the question is, how much data can I really observe? How much of testing can I do, practically speaking? So there is this question of practicality and this question of making claims about the whole population. So we need to balance this point of risk versus resource. So this we had done, if you recall, we started with risk minimization versus resource utilization through the bridge problem, and we took a peek at interval estimate through the sand pile problem. So the first problem that we discussed was how many cars can be allowed to ply at a time on a bridge. So if we allow very large number of cars, the bridge may break. If we allow too small number of cars, then we are not utilizing the resource optimally. And we know that the bridge breaks when this condition is satisfied, when the total number of the weight of the total number of cars exceeds the tolerance value, the bridge will break. And if you recall, we understood that both the left-hand and right-hand sides of this inequality are normally distributed. Therefore, this comparison is possible. Both are normally distributed, and we make use of this fact in finding out the number of cars that can be allowed on the bridge. The other problem which we looked at was the percentage of sand grains whose size falls in a particular range. And that question is important for another field of activity, for painting, because sand particles are used in painting. So they should be in a particular range of size. Only those particles can be used. And here we saw that scientific knowledge outside data, okay, comes to our help. Kolmogorov's law of fragmentation, which said that the size of particles resulting from fragmentation follow log normal distribution. Okay, and this was used for interval estimate by making use of machinery of normal distribution. So now we again look at computing of z-score and how this is used for building confidence in our observations. How do we proceed towards building confidence in our observation through z-score computation and interval estimate? So we have seen that any normally distributed random variable x can be converted to a standard normal form. So I take the random variable, subtract the population mean, divide it by the standard deviation, and I have what is called a standard normal form for which the mean is 0 and standard deviation is 1. This is given the notation z. And the quantity that we deal with always, given the standard normal curve, is the so-called z-score. So this red arrow here, just trying to make sure that everybody is seeing the standard normal curve. Can somebody verify?
Yes,
looking
sir.
at the standard normal curve. Okay. So here this red arrow is pointing to capital Z equal to small z. Let us just remember once again that in probability, the random variable is given the capital letter, and the value of the random variable when indeterminate is given the small letter symbol. Okay, so capital Z is random variable. Its value, which is not known, is small z. Okay. Now, now the area from minus infinity to capital Z equal to small z, this area is called the Z score, and a very important quantity for us, because that area from minus infinity to small z is the probability of the interval minus infinity to small z, and the probability of the random variable picking up value from that range. So that area is all important. It is called Z score. Now, the interval probability, where Z takes value from A to B, A is the lower side of the interval, B is the upper side. That interval probability can be estimated, as you can easily see, by taking the Z score value at B, taking the Z score value at A, and subtracting Z score value at A from Z score value at B. So this area under the curve from Z equal to A to B is the interval probability. Okay, and that can be found out by this notation phi B minus phi A, the cumulative probability, which we discussed last time, but 2 weeks have elapsed, and therefore there is no harm and at reminding ourselves of cumulative probability distribution. So cumulative probability distribution is the area under the curve from minus infinity to that particular value of the random variable. So phi b is the probability of being in the range minus infinity to small b. Phi a is the corresponding probability value at z equal to a. Now phi b minus phi a will give me the interval probability. Now, why is this important? Because we would like to make use of this for confidence intervals. And PDF, you will recall, is probability density function. Cumulative distribution function is CDF, and there is an integration differentiation relationship between them. So let's see its application to some questions that we ask always, in particular, the 95% confidence interval, the so-called 95% confidence interval, which comes in our activity very frequently. Now, the probability of Z taking a value from minus infinity to capital V is minus infinity to V integral 1 by root 2 pi e to the power minus y square by 2. So here the mean value is 0. That's why e to the power minus y square by 2 plus y minus mu to the whole to the power 2. And 1 by root over 2 pi sigma. Now sigma is equal to 1 here. So let us note this expression a little carefully, because we'll have to make use of this in finding out how many cars can we allow on the bridge. Okay, let's look at this expression a little carefully. So probability that Z is less than V, that means minus infinity to V, is integral minus infinity to V 1 by root 2 pi e to the power minus y square by 2. So this is the area under the standard normal curve from minus infinity to V. So this is the Z score value at V. Okay, this is the Z score value at V. So let's keep note of this and remember this: probability of Z less than V. So now this integral cannot be given a closed form algebraic expression easily. Okay? Cannot be given an algebraic expression easily. So I'd request everybody to mute your mics, please. Yeah. So this is the z-score at V, and z-score values, you recall, are given in the form of standard normal probability tables. So the tables are to be read in the following way. The rows give the values up to first decimal place and the columns up to second decimal place. So if I want to know, for example, the z-score at 1.42, I'll go to 1.4 row wise, z equal to 1.4, and go to 0.02 as the column. So the intersection of 1.4 and 0.02 gives me 0.9222. So the z-score value at 1.42 is 0.9222. That means the area of the standard normal curve from minus infinity to z equal to 1.42 is 0.9222. Okay, so the interval probability from minus infinity to 1.42 is 0.9222. Now, how do we use the z-score table? We illustrate how to use the z-score table by finding out the interval that gives me 95% probability, okay, 0.95 probability. What is that interval? In the z curve, the standard normal curve, what is that interval which gives me, around the mean, of course, around the mean, which gives me area of 95% or interval probability of 95%. This is from minus 1.96 to plus 1.96, about 2 sigma, minus 2 sigma to 2 sigma. So can I really verify this? I verify this from the standard normal table, the z-score table. So I see here in the z-score table the value of 1.96. Okay, the value of 1.96 is 1.9 row and 0.06 column. So here the value recorded is 0.975. So the interval probability from minus infinity to plus 1.96 is 0.975. Okay. Now I do a bit of mathematical calculation. Phi 1.96 is given to me as 0.975. Okay. I want to know phi minus 1.96. That is equal to 1 minus phi 1.96. This is because of the symmetry of the normal curve, standard normal curve. So the value from minus infinity to minus 1.96 is equal to 1 minus phi 1.96. That is because of the symmetry. The value from minus infinity to minus 1.96 is exactly equal to value from plus 1.96 to plus infinity because of the symmetry. So the value from minus infinity to 1.96 is known. So 1 minus phi 1.96 is that probability. So to get the probability from minus 1.96 to plus 1.96, I do this mathematical operation. It is equal to 2 into phi 1.96 minus 1. And phi 1.96 is 0.975. So 2 into 0.975 minus 1 is 0.95. Okay. So the interval probability from minus 1.96 to plus 1.96 is equal to 95%. So we have found out the 95% confidence interval limit. And the purpose behind this short discussion, was how we can make use of the z-score table, the technique of making use of the z-score table. So the z-score table works. It gives me the value of an interval probability. So now I can make use of this technique to find out that important parameter. Okay, the city authorities want to know how many cars, when allowed simultaneously on the bridge, will make the bridge unsafe. That is the question we were handling, and we would like to know the mathematical steps involved in computing this. So the number of cars that can make the bridge unsafe is called n unsafe. Unsafe, the lower right suffix. N unsafe is what we are interested in. Now each car's weight is given to be normal with mean as 3 and standard deviation as 0.3. So cars' weights are normally distributed. We know their mean and standard deviation. So we'd like to invoke the central limit theorem. A version of the central limit theorem, there are many different versions, tells me that the sum of normal variables, normally distributed variables, Gaussian random variables, is again normal with mean and variance being sums of individual means and sums of individual variances. Okay, so the total weight of cars is normally distributed with n into mu as the mean and n into sigma square as the variance, equivalently sigma root n as the standard deviation. So the total weight of cars is normal with mean as 3n. N is something I don't know. N unsafe is what I want to find. Mean is 3n and sigma square is 0.09n, where n is the number of cars and 0.09 is 0.3 square. Mu car is 3 and sigma car is 0.3. So this I know for the left hand side of the inequality of unsafety. And W tolerance also is known to me with mean as 400 and standard deviation as 40. So the screen shows W tolerance and the curve. Can somebody verify this? The screen is showing W tolerance.
Yes, sir.
Yes, okay. And the bridge is damaged when W total is greater than W tolerance. That is fine. W total greater than W tolerance is W total minus W tolerance greater than 0. So we are doing these mathematical steps and not jumping to n unsafe to teach ourselves the technique of this probabilistic analysis. Okay, the bridge is an instructor. The bridge problem is an instructive situation which will help us in our NLP research. Okay, these techniques can be transferred when we want to apply it to our NLP work. Okay, so W tolerance should exceed, W total should exceed W tolerance. Equivalently, W total minus W tolerance should exceed 0. Okay, so we are interested in finding the total number of cars allowable on the bridge given the symbol n unsafe. And n unsafe, where does it appear? It appears in W total. Okay.
It seems that sir's connection is frozen.
Yeah, looks like that.
Am I audible now?
Yes, sir, you are.
Yeah. Momentarily, it was connection was lost. Is the screen visible?
Yes, sir, it is.
Screen is visible. Okay. So we want to know when the total weight will exceed the tolerance limit. Total weight is a function of n unsafe. And we are interested in the technique for finding out n unsafe. So how do I cast the problem in terms of probability? Okay, so we're interested in the probability of W total exceeding W tolerance. How much probability? Okay, so I assign for myself, it is a hyperparameter for the situation, that this probability should exceed 0.1. The probability of W total exceeding W tolerance should be more than 0.1. So there are two greater than symbols. Let us not get confused. The event is W total exceeding W tolerance. That is the event. The probability of this event should exceed 0.1. So two greater than signs. Okay. So W total exceeding W tolerance is cast as W total minus W tolerance greater than 0. And the probability of that event should be more than 0.1. So it is instructive for us to note these mathematical steps, without which we cannot find n unsafe. Now let us look at the mathematical steps. This particular discussion today is on the mathematical steps. Okay, looking at the mathematical steps, which is useful for our work also in our research. So now I have to deal with W total minus W tolerance. Okay, this is the instructive part, W total minus W tolerance. W total minus W tolerance has mean 3n minus 400. Okay, this is again by the properties of expectation and property of variance. Let me see, yeah. So W total minus W tolerance is now my new random variable. W total is normally distributed. W tolerance is also normally distributed. Okay. Now the sum of two normally distributed random variables has mean as the sum. Okay. The proof can be done. We can do it at some point of time. So the mean of W total is 3n. The mean of W tolerance is 400. So the mean of W total minus W tolerance is 3n minus 400. What about the standard deviation? The variance of W total is 0.09n. Okay. The variance of W tolerance is 40 square, 1600. Now, while means get subtracted, variances add up. Okay. So even if two random variables are subtracted, their variances do not get subtracted. Their variances add up. Okay. This is intuitively understandable. I have a proof also going forward. Okay. So now this W total minus W tolerance, which is a normal variable, has mean 3n minus 400 and standard deviation root over 0.09n plus 1600. Please note the mathematical steps. Okay, how mathematical steps are being used to arrive at the answer. So first thing we did was we subtracted two normal variables. Next thing we did was we found out what is the mean of this new normal variable. And we found out the standard deviation of this new normal variable. We subtracted the mean and divided by the standard deviation. Now we are in the realm of standard normal variable. Standard normal variable whose mean is 0 and standard deviation is 1. And now I can make use of the z-score. So please note this technique and try to use it in your research. Okay, note this technique of subtracting the mean and dividing it by the standard deviation, and how a new normal variable, a new random variable is constructed from the constituent random variables pertaining to the situation. We want to know when does W total exceed W tolerance. So all these steps are towards this. Now I want W total minus W tolerance to exceed 0. So I subtract 3n minus 400 from this quantity left hand side. I do the same to the right hand side. I divide it by standard deviation, on both sides. So now on the left hand side of the inequality, I have a Z variable. I have a standard normal variable on the left hand side. On the right hand side, I have a quantity which contains my required number of cars that can be allowed on the bridge simultaneously. So since the left hand side is a Z score, I write it as Z. So Z should exceed the quantity on the right hand side. So Z should exceed the quantity on the right hand side. Okay, I am coming to that step now. Now, Z exceeding a particular value cannot be dealt with using the Z score. Okay, Z score is always for minus infinity to that particular value of Z. So Z score is always in terms of less than a particular value. We have a situation where Z is exceeding a particular value. But that is not a problem. We can make use of the symmetry of the normal curve. Z exceeding a particular value is equal to 1 minus Z being less than a particular value because of the symmetry of the normal curve. So that is fine. So we want the probability of Z exceeding a particular value to be greater than 0.1. Okay, to be greater than 0.1. So this is my original formulation. The unsafety situation is the total weight exceeding the tolerance weight, and the probability of that event should be greater than 0.1. Okay, so this is the formulation, and I have the standard normal variable exceeding a particular value. So now the probability of Z exceeding a particular value is equal to 1 minus probability of Z being less than that particular value. We want that Z probability of Z greater than V should be greater than 0.1, or 1 minus probability of Z less than V should be greater than 0.1. See that greater than symbol has been converted to less than symbol. Or probability of Z less than V should be less than or equal to 0.9 by algebra. Okay, I take one to the other side and this is there. So now probability of Z less than V should be less than or equal to 0.9. If I consult the Z table, where do I see 0.9 as the probability value? This value happens to be 1.29. Okay, look at the row 1.2 and 0.09 as the column. Here the probability value is 0.9. I have put a red circle around this. Somebody please verify that you are seeing that red circle and within that 0.9 value.
Yes, sir.
Right? Right. So the probability up to V to be 0.9, that will make V as 1.29. Okay, V is 1.29. Now we are almost there. V is 1.29, and what is V? V is nothing but minus 3n minus 400 divided by roots 1600 plus 0.09n. So the right hand side is a function of n, in particular n unsafe. And when I solve this equation, I get n equal to 117. So I can, if I allow 117 cars simultaneously to be on the bridge on an average, will display unsafe behavior. Okay, what is the meaning of that unsafe behavior? The probability of breach breaking will exceed 0.1. Okay, that means in 100 such cases, of 117 cars simultaneously being on the bridge, 10 of those cases will have the bridge broken. Okay, on an average. If we do this many times over, then 10 out of 100 cases will see the bridge breaking. And what is the situation? We have allowed 117 cars on the bridge. Okay. So through this exercise or through this discussion, what we have shown is the technique of finding a quantity of interest by consulting the Z-score table and casting our requirement in probabilistic terms. Okay, so the two messages conveyed through this discussion is this. One is reading the probability table, okay, the Z-score table, and casting the problem as a probabilistic question. The event is W total exceeding W tolerance, which is equivalent to W total minus W tolerance becoming more than 0. That is the event. Why is it probabilistic? It is probabilistic because the number of cars and their weightages are also probabilistic quantities. Okay, everywhere it is probability, not definite deterministic values, but everything is a probabilistic quantity. And this value, the probability of this event happening, should exceed 0.1. Okay, 10 out of 100 such cases will lead to breach breaking. We are interested in this situation, and the situation is a very practical one, intuitive one, understandable. See how it is given a formal shape through probabilistic treatment and making use of the existing knowledge of the Z table, the symmetry of the normal curve, which allows me to deal with both greater than a value and less than a value, reading of the Z-score table, and arriving at the unsafe value by solving an equation finally. Okay? So this is a very instructive exercise and is analogous to our situation. How many words should I pause tag? Okay, how many words should I pause tag to make a claim that my precision is 95% with my trained model, which has learned how to do part of speech tagging? How much of corpora should I pause tag to be able to make a claim about the accuracy of the system? Okay, so that question is very similar to how many cars can I allow on the bridge not to cross safety limit. So that is the analogy, and it made use of central limit theorem, but I don't think we have time. But let me just give a glimpse of what is going to come. What is going to come is this: the statement and proof of central limit theorem. The statement is this: let x1, x2 up to xn be n independent random variables, each with mean mu and variance sigma square, and also let Sn be the sum of these random variables. Then this Sn star, which is Sn minus n mu divided by sigma into root n, is a standard normal variable. This is the central limit theorem. Okay, the statement of the central limit theorem is this: take n random variables, each of them has mean and standard deviation sigma, identical mean and sigma. Look, take their sum. This sum minus n mu divided by sigma root n is a standard normal variable. Okay, the crux of the theorem is this, that last part. This summation this summation minus n mu, mu is the population mean, divided by sigma root n is a standard normal variable. Okay, that is the main point of the central normal theorem. We are not saying anything about the nature of distribution of x1 to xn. We are looking at only the sum, and that sum minus n mu divided by sigma root n is a standard normal variable. That is very beautiful, right? That is not something I had expected. So n random variables, their sum has a particular behavior as n becomes larger and larger. Okay, and that takes me to the realm of normal variable and allows me to use all the theorems and lemma of normal variable to make claims about parameters. Okay, and one parameter we are interested in is accuracy of my machine learning model. Okay, so that is the connection, and we'll need a few lemma here: variance of subtraction of random variables and expectation of sum of random variables, variance of sum of random variables. All these proofs are given here. These proofs are elegant and simple. We would like to do them. So at this point of time, I would like to stop and take questions. So if there are questions on the chat box, I don't know.
Hello, sir. Aman this side. I have one small question.
Please.
So, this central limit theorem. So, x1 to n, xn, they can obey any distribution themselves, or they need to be perfectly random.
No, they can obey any distribution. Only thing is that n should be more than 30. Okay, n should be more than 30. I'll see if some proof for this can be given. N should be more than 30, and x1 to xn can be any distribution. But if x1 to xn individually are normally distributed, then that restriction of n greater than 30 is not necessary.
So that answers my question.
Okay. Any other question? I would request people to put questions in the chat box. Any question that comes to your mind. I mean, keep putting them, and I would love answering them. But please ask questions if you have any.
Sir, okay, so you told that x1 to xn be the independent random variables and they might have a different probability distribution, but
Right.
also you told that x1 to xn they should have each with a mean mu and variance sigma square. So their mean is same and variance is also same, right? Then
Right.
how we can say that they have a different distribution?
No, I mean their nature can be different. One can be binomial, another can be Poisson. Okay.
Okay.
So any random variable can have population mean and standard deviation. Right.
Yeah. Okay, got it.
Any other question? Okay. So looks like there are no more questions, but I encourage everybody to put your questions on the chat box as the lecture goes on. Please do that. No question is trivial or wrong or not to be taken seriously. Every question is important. We'd like to do that. So I'll just close the lecture today with final remark. I hope you have taken note of how a practical situation is converted into a formal probabilistic question, and how there are machinery to take us to standard normal distribution that allows us to pick the instruments from normal distribution. This is the main message of the discussion today, and we would like to apply it in our research on NLP.
sir. So
Yeah.
Aditya here.
Who is this, please?
Aditya here.
Can't hear you clearly.
Hello.
Yeah.
Yes, sir, Aditya here. I have one
Yeah.
question.
Yeah.
Yeah. So, sir, the major purpose of normalization is when the parameters are in
No,
different.
wait. We have to use correct terms. Normalization or major purpose of going into normal distribution, you're saying?
No, normalizing the data.
No. What does normalizing the data mean?
So, like converting the given parameter,
Hmm.
like subtracting the mean from it and dividing by standard deviation.
Oh, yeah. Okay. Converting
Normalize.
into a standard normal variable. Okay. Yeah.
Yes, sir. So the major reason behind doing this is when the parameters are in different ranges. Like one parameter is 1 to 10 only, other is like 500 to. So
No. What does that mean? No. Wait. What does that mean? The parameters have different range, you are saying.
Yes, sir. I can give an example.
Hmm.
So suppose there are two parameters like age, which can be around 1 to 100. Okay.
Okay.
And other parameter is like salary, which
Hmm.
will be in around lakhs. Okay.
Hmm.
So while using this data as it is, so it might happen that due to the larger values of salaries, it will be getting more importance, right? While calculating the final result, while multiplying.
No, wait. Importance means you're making some decision, and that decision is a function of age and salary.
Yes,
So
sir.
let's say I'm deciding on loan application sanctioning. Okay,
Yes, sir.
and I see that the decision to whether sanction the loan or not is a function of age and salary. Okay, fine.
Yes, sir. So this way salary will always dominate, right?
Why? Because the salary is increasing? No, I don't see the connection.
So because salary will always have high values, high value ranges.
Okay.
So by treating it as a weight, like multiplying by weight, so it will be always getting higher importance that.
So because of their values, they will be the dominating variables. That's what you're
Yes,
saying.
sir. Yes.
Achha.
Right.
And now if I subtract the mean and divide by standard deviation, then both age and salary are becoming standard normal variables.
Yes, sir. So is
Okay.
that the major reason behind normalizing the data?
No. The major reason is to be able to use the Z-score table.
Z-score table. Okay.
Yeah.
Yes, sir.
Yeah. I want to do interval estimate, and therefore I want to convert them into standard normal forms.
Okay. Yes, sir. Got it. Thank you, sir.
Anything else? Any other question? Okay. So if not, then we'll finish the lecture. I would request the information extraction group 2 people to connect on the Google Meet link for our research update. Thank you.
Thank you, sir.
Thank you, sir.